Well, good afternoon, everybody. I thought I'd start maybe 10 or 15 seconds earlier than the 3 o'clock scheduled start time. Welcome to the MS Distribution and Siklu, everything you need to know about Terragraph that you didn't know you needed to know, but you're going to find out by the end of the session. We do have quite a few of you sat eagerly waiting for the lovely Daniel to tell us some information. Tell you more about Daniel in just a second. And of course, as always, when I start one of these sessions, you get to listen to me ramble on for moments and moments and moments whilst we wait for other people to join in with us. I usually pick on my good friend Jerry from Scotland and say that we're waiting for Jerry because it's only 1 or 2 minutes past 3 and he'll be struggling back from the pub. So we've got to give him a couple of seconds to get back and get signed up. And I'm sure he'll be with us very, very soon. As is usual with when we run webinars with Siklu and MS Distribution, if you'd like to put any questions to us in the questions section as opposed to the chat section, that would be really lovely if you could. So any questions you've got, open up your dialog box, type them into the questions section. I'll marshal those questions so we don't disturb Daniel when he's doing the presentation too much. We'll come back to you with all of the answers that we can come back to you with during and at the end of the session, depending on how Daniel wants to deal with those. And if there are questions that we don't have answers to immediately, of course, we will find those out and make sure that everybody has exactly what they need, hopefully by the end of the week, although we are Thursday today, so it might be, oh, and of course, I forget, we're with Siklu, so their weekend starts tomorrow. Might be early next week for answering any questions that you might have that we can't answer whilst we're live on the webinar. So we will get into Terragraph in a moment. Usually when I do this rambling stuff, I go on a little bit longer than 2 minutes. So I probably need to make some stuff up about how wonderful Terragraph is. Interestingly for you all, I can tell you that there are currently some deployments live across the UK, and those deployments are going exceedingly well in the field. And if you need to know any more about that, obviously feel free to either talk to myself or Daniel offline if you wish to do so. We can help you out with that kind of thing as well. So we will start in a few moments' time, but we will just give people, as I say, just a little bit longer to try and join us. Questions, as I've already said, and sorry to bore those people that have been with us for a little while. Questions, if you have any questions, please put them in the question box, not the chat box. I will marshal the questions for everybody, and we'll get those answered for you towards the end. So now I have the ultimate time waster whilst we're waiting for people. Here we go. Welcome to Adam and Anthony and Chris and Claudio and Dave and David and David and Ettore and Hardus and Gustavo and Ian and India and Jay and Jerry and John and John and John and Jonathan and KM and Lee and Liam. You see, I'm going to keep going. Mark, Mike, Morgan, Nick, Nigel, Paul, Pedro, Peter. Have you any idea how many people are with us, Daniel? Sam, Scott, Stuart, Tim, and finally on the bottom of the list, but by no means last, in many ways, is Todd. I've actually seen some other people pop in just as I was going through the list. So there's plenty of us around. We're going to learn some really interesting stuff this afternoon with Daniel. And as we're approaching 5 minutes past now, and we'll probably start at 5 past, I would like to personally introduce Daniel to you all. If you haven't met Daniel before, Daniel is one of the engineers that I have the utmost respect for in our radio community, and you're all part of our radio community. What Daniel doesn't know about the radios that he works with isn't worth knowing about. In fact, you could probably write on the perforations around the edge of a postage stamp, if indeed postage stamps still had perforations. Unfortunately, they don't, because they're now sticky things, and you no longer got to peel them apart and lick them and stick them. Anyway, without further ado, it does give me great pleasure to have Daniel here with us to explain to us all everything that you ever wanted to know about Siklu Terragraph. Daniel, over to you, my friend. I'm going to turn my camera off. I might even mute myself to shut myself up. Thank you so much for taking the time to join us today. I really appreciate it. I'm sure I'm going to learn some stuff, and so will everybody else. Here you go. Quiet.
Thank you very much, Ian, for that amazing introduction. I hope to be able to live up to half of the things you said. And thank you, everyone, for joining. We've got quite a number of you, so that's very nice. I'll try and do my best to entertain you for the next 50 minutes or so and tell you things that you may not have known. Just before we start, I also would like to thank my colleagues in marketing, Siklu Marketing, MS Distribution Marketing, for putting all this together and for contacting all of you, letting you know that this event is on. I know that's not a simple thing, so thank you. And let's start. So I've done a few of these webinars already for MS Distribution, and the feedback I tend to get is that people like it to be a little bit more technical and less sort of product sales oriented. So I've tried to do my best again with Terragraph, tell you some of the more interesting technical aspects of it, but I will talk a little bit about specifically the Siklu portfolio, just because it helps to put some abstract ideas into context. So this is a sort of bird's eye view introduction of Terragraph in our portfolio at Siklu. My name and email address are there, so feel free to contact me with any questions. Okay, so I'll divide this presentation broadly into three. So first, I'm going to just explain a little bit about the technology and, like I said, touch on the Siklu portfolio, just because I think it helps explain some of the concepts. Then I'll talk about some operational concepts, because Terragraph is not a trivial system. You need to know quite a few things to make it work properly. And then last, but perhaps most interestingly, I'll talk about network design considerations. Okay, just before I do though, a minute about Siklu. For those of you who don't know Siklu, so we're a company based in Israel. We've been around for about 14 years now, and I'd like to think that we revolutionized the millimeter wave market. I don't think people used millimeter wave radios before Siklu came along, so I'm pleased to say that now they do. I live in North London, and I often walk about, and all of a sudden there's another Siklu radio. So it's a great feeling to know that we've been able to contribute somewhat into introducing this technology into the UK and, of course, other countries, as you can see here. Okay, so the first part of this presentation is just to introduce the technology. Okay, so I think the most important thing is to differentiate two terms that I'll be using. So first of all, there's the multi-hole Terragraph, which is the name of a Siklu portfolio of products. So these are all similar to, if you know, our other radio products. So they are wireless switches, if you like, but they are able to implement broadly speaking, three types of topologies. So point-to-point, point-to-multi-point, and also mesh-type topologies. They operate at multi-gigabit speeds in the 60 gigahertz spectrum, which we'll talk about a little bit later. And all these products are Terragraph certified. So that immediately raises the question, what is Terragraph? So Terragraph is a gigabit wireless technology developed by Facebook, now called Meta. They did this under a broader umbrella called the Telecom Infra Project, or TIP. And they basically put together an ecosystem of, dare I say, the best wireless experts in the world, including Siklu, to try and develop this system in the best possible way. So we're privileged to be part of this. And the physical layer and the MAC layer, if anybody is interested, is now standardized as an IEEE standard, as you see here, 802.11ay. So if you as an analogy that might help you understand this better, Terragraph, I always like to say, is like the blueprints for an engine. And then vendors such as Siklu took those blueprints, built the engine, and actually built the whole vehicle or the whole product around this engine. So hopefully this helps you understand this a little bit. And on we go. In terms of applications, basically, I think you probably are all aware of key applications for millimeter waves. Here in the UK, we see a lot in smart cities and network connectivity, be it ISPs or business-to-business broadband connectivity. In other countries, we also have mobile backhaul and IoT applications. Security applications are also quite strong here in the UK. So basically, wherever you want to connect devices via broadband, Terragraph might be the right technology for you. So what are the key advantages of Terragraph? Why would you want to use it in particular as opposed to other things? So first of all, it's good to know it's an industry standard, as I've just explained, driven by quite a powerful player and an ecosystem of powerful players under the TIP, the Telecom Infra project. So when you choose a Terragraph product, you're basically choosing something that's widely supported in the industry, as opposed to some company-specific proprietary technology that may disappear tomorrow together with that company. Also, because it's widely adopted, we can take advantage of economy of scale. We're able to get components and subsystems at great prices because this technology is very popular. The more people buy, the more the prices decrease. So this is very good. Another key advantage is powerful interference immunity. This is facilitated both through the physical, I would say, aspects of the wireless transmission, so very narrow and focused beams, naturally decayed transmission, and transmission that's blocked by any obstructions such as vegetation and building. So this is all a consequence of the physical, I would say, propagation at these frequencies. But there are also some specific aspects to Terragraph which enhance this even more. So things like synchronization. Terragraph requires synchronization to satellite, and we'll talk about this, multiple RF channels and other protocol-specific interference mitigation tools. So we'll talk about these in more details in a little while. Another key advantage for Terragraph is that it's able to support mesh networks, and in particular redundant paths. So different vendors go about this in different ways. For Siklu, we support this with the help of SmartHall, which is a collection of software tools that I'm not going to go into in this presentation, but if you are interested, speak to us and to MS Distribution. Now, I'd like to set expectations a little bit in terms of range. So range in Terragraph is determined by the type of antennas used. Now, originally, the Terragraph envisioned using beam-forming antennas. Now, beam-forming antennas are great. For those of you who don't know, they're antennas that are able to electronically steer a narrow beam within a wide sector. So this is unlike sectors that you perhaps are familiar with at 5 gigahertz or other low frequencies where the antenna illuminates an entire sector. So this is different here. Here, the transmission beam is very narrow, but the transmission beam is steered, electronically directed within that sector to the desired location. So this is great, and this was the original idea. However, unfortunately, the regulators, in their wisdom, placed a very strict limit on the radiated power of beam-forming antennas, and that restricts the range. So if you'd like to use a beam-forming antenna, because it's great, very easy to align, you don't need to worry about it too much, you just deploy it and it does its own thing. You have to be content to use it over just several hundred meters because it's due to this regulatory constraint, it's just not able to transmit any more power. Now, to get around this, what we do is we, on some of our products, so we give you the option to use parabolic antennas. Now, parabolic antennas are not subject to the same limitations as beamforming antennas are, and therefore the radiated power can be a lot stronger, and therefore the range is all of a sudden extended to a couple of kilometers. So this is great. But on the flip side, if you are using parabolic antennas, then you have to manually align them. For those of you who are familiar with our ether hole product range, you are probably experts at antenna alignment, and this is very similar. So beamforming antennas for the shorter range and parabolic antennas for the longer range. And we'll discuss this in a little bit more detail later on. Okay, I mentioned the 60 gigahertz spectrum. So just to say, this is sometimes called a V-band. And in the UK, this is now licensed. Now, I know this might surprise some of you because it used to be unlicensed for many years, but I think it was in 2020 that Ofcom decided to make this a licensed band. However, it's very lightly licensed. It falls under what they call an EHF license, or extremely high frequency license. And basically, once you get this license, you have the right to access the 60 gigahertz spectrum, and you can deploy as many links as you like. So basically, it's a one license per organization. So you only have to apply for it once as an organization, and you do not have to register every single link as you might do in microwave or in E-band, if you're familiar with that. The cost of this license is £75, and you have to renew it every 5 years. So if you are using Terragraph radios or any other 60 gigahertz radios, please apply to Ofcom to get your EHF license. That's the thing to do. Okay, now I said here use the spectrum wisely. This is because 60 gigahertz is heavily impacted by attenuation due to oxygen in the atmosphere. And you see this graph here, which shows the specific attenuation. So this is attenuation in dB per kilometer. And around channel 2, that can be quite high. It's about 14 or even 15 dBs per kilometer. So this slightly varies depending on things like temperature, air pressure, and humidity or water content in the air. So I've plotted this for what we call a standard atmosphere, but other atmospheres are very similar. And so what you can see here is that in channel 4, for instance, there is less of attenuation due to oxygen. So if you like to go to longer distances, opt for channel 4 as opposed to channel 2, for instance. This is just something to be aware of. Okay, so this was a bit of a preamble, and I'd like to dive a little bit deeper now into the Terragraph technology. So the first thing to talk about is explain the network elements within Terragraph. So this is important because I'll keep referring to these terms again and again throughout this webinar. So first we have the distribution nodes, which some people abbreviate as DN, right? The N acronym for distribution node. And the distribution nodes that are shown here in green in this little drawing, they form the backbone of the network. So distribution nodes can connect to other distribution nodes, right, as you see here in green. But distribution nodes can also connect to client nodes, which I'm showing here in orange. So these are client nodes. Now, what are the client nodes? Client nodes are the endpoints in the network. So they could be a single family home, or they could be a lamppost where you've got maybe a CCTV camera. So basically, they're like stubs within your network. So a client node connects to a single distribution node, and distribution nodes connect to other distribution nodes as well as client nodes. So basically, DNs and CNs together make up the mesh network. So here you are. So remember, distribution nodes and client nodes, and we'll talk about them more as we go along. Now, as I said before, I didn't mean to do this initially, but I felt it would be better to do a very brief introduction to our portfolio, just because it will help place things in perspective for you, I think. And so when we look at the portfolio, there are various aspects by which we differentiate the different radios. So I put them on this slide. So first of all, we have the type of Terragraph network elements. So a radio can be a distribution node or a client node. And to make things easy for people who just need point-to-point, we've also got a special arrangement for point-to-point, but let's just concentrate on distribution nodes and client nodes for the moment. I already mentioned antenna types. So beamforming and beamformings can either cover a single sector, as you see here in the middle of the slide, so that's a 90-degree sector, or if you put several of these sectors together into one device, as we see here, 4 sectors, then you can achieve full coverage of 360 degrees. So beamforming antennas are obviously required for the distribution nodes because the distribution nodes make multiple connections. So in order to make multiple connections, you need to have beamforming antennas because the narrow beam needs to be able to quickly jump from one connection to the other. So all the distribution nodes have beamforming antennas. Client nodes, some of them have beamforming antennas and others have parabolic antennas, as you can see here. Parabolic antennas, like we say, what I said before, have to be manually aligned. And another differentiator in the portfolio is the Ethernet ports, the number of ports, the types of ports, and the speed at which these ports operate. So is it 1 gig or 10 gig? For example, is it copper, is it fiber, and so on. So these are the main differentiators, and I'll speak about them or mention them as we go along. Here is a little table to hopefully help you reference some of our radios that I may mention throughout this presentation. Again, not because this is specifically about the portfolio, but just generally to refer to a particular type of network element. So at the top of this table, we have the distribution nodes. They're all beamforming antennas. Some are 4 sectors. That's a more interesting one, which I'll devote most of today to, but there's also a single sector distribution node with a beamforming antenna. Then we have some client nodes. Some are beamforming, some are parabolic, and some can also be used for point-to-point. Okay, good. Enough said about the portfolio, and that was part 1. Now, I'm not sure if there are any questions. Ian, I know you're monitoring the questions. If there's anything that you think is urgent or is pertinent to what I'm discussing, please feel free to interrupt. Maybe if there's some more general questions, we can keep them till the end.
Thank you, Daniel. There wasn't a question, but there is now.
Okay.
Are beamforming antennas better for CCTV poles where they move and shake in the wind? There's an interesting question for you.
Yeah. So yes. So beamforming beamforming antenna beams are generally wider than parabolic antennas. So they're about 5 degrees wide. So they're quite tolerant to movement. However, with a half-foot parabolic antenna, the beam width is 2 degrees, and that also works quite well on lampposts. So we know lampposts are actually designed to be a little bit flexible for elastic collision, if you like, to be a little bit safer to collide into. And so the half-foot parabolic antenna works quite well. The beamforming works quite well. I wouldn't put larger parabolic antennas on a lamppost.
No, indeed. Thank you for that question, Peter. Hopefully that answers the question. If not, please put a subsequent question in. Tim asks, is the gain and RX sensitivity of the 90-degree sector the same as the N366 segments?
Yes. So the distribution node with 4 sectors simply comprises 4 sectors. So the performance of each sector is the same, and they're the same also as the single sector distribution nodes. They're the same sectors. They're just put together.
Brilliant. Ettore says, are we making the presentation available for download? I should have said at the start we are recording, and we will make the recording available for everybody. So that's good news. See, there's a question I can answer. And I think I might answer the next question as well, Daniel. So you'll have to examine me on my answer and tell me whether I'm right or not. Pedro says, for long range, what's the best channel to use using T280s in PMP mode? I'm going to go channel 4. What do you reckon?
Absolutely, channel 4. So channel 4 has lower oxygen absorption So that's a channel to go.
Brilliant. We've done all
Thank
the
you,
questions.
Ian. I see you've been listening. So that's great. Thank you.
Sorry. There is another question. I'm not sure I should actually tell you who this is from, but it's from somebody called John Talton. And he says, how much Siklu can I buy? And the answer to that, Mr. Talton, is how deep are your pockets?
All right, super. Thank you very much for that, Ian.
We do have just one more. Sorry, Daniel. Sorry to interrupt.
Yeah.
Are there also access antennas on the devices? I believe the node are both integrated access and backhaul. Now, you might cover off how the node actually operates in a little bit, so I think you'll probably answer that in the presentation.
Yes. Yes, so that I will address that. Yes.
Okay, I'll leave you with it for now.
Thank you very much, Ian, and thanks everyone for asking questions. It's great to know that you're engaging and I'm not talking to my screen, so this is super. Right, so the second part of this presentation it now becomes a little bit more interesting and more technical, and these are the topics that I'm going to cover in this second section. So I'm going to talk about synchronization, which I briefly mentioned before. I will explain what the POP node is and how links work in Terragraph, and then just mention some other technical bits like node names and SSID and password. Okay, so let's start with synchronization. Now, do bear with me. There are some how-tos on these slides. This is because these slides are taken from a new e-learning course that we are about to post on our partners portal. As you see, I didn't clean them up properly, as the note here says, but let's just ignore that. So I'll not go through all the details in these because this is, like I said, intended as e-learning, and we're just doing sort of an introduction at the moment. So distribution nodes, and this is true only of distribution nodes must be synchronized with the GPS satellites. Basically, they need to be able to recover the clock that's transmitted by the GPS satellite. Now, in order to be locked, a radio needs to see at least 3 satellites. And on the webGUI, just so you know, we do show you how many satellites that the radio can see. And so that really means, once I say to you that the radios need to see the satellites, it really means that the radios are suitable only for outdoor installations, right? Because obviously indoor, they will not be able to see the sky and therefore the satellites. Now, sometimes that may create a problem when you're installing radios at the foot of a very tall building, or perhaps very close on a lamppost, very close to the lamppost canopy. Those things can obstruct the sky and can maybe limit the number of satellites that are seen. So in that case, if you are installing next to a wall and you're experiencing that kind of problem, just use a bracket with a longer arm to distance the radio from the wall or on the lamppost. Just take the radio down away from the canopy to reduce the shadow, if you like, cast by the canopy. It's just some practical tips. Now, a lot of you will want to do indoor testing, so you receive some radios from MS Distribution, and the first thing you want to do is play around with them, make sure they work properly. So yes, you can test them indoor, but only in quite limited scenarios. And what do I mean by limited scenarios? Things like just point-to-point connection, or maybe point-to-multipoint in a single sector, not multiple sectors. So if you'd like to do that, you can. You just have to change the synchronization mode in the radio to what we call no sync, and that is a kind of a testing mode. So just be sure if you are trying to lock any links or do anything indoor, you must disable this GPS synchronization and go to no sync mode, otherwise things won't work for you. Okay, so that was synchronization. Next, I'd like to talk about the POP node. In Terragraph terminology, that's called the POP DN, or POP distribution node. So within a Terragraph cluster, and what do I mean by a cluster? So a cluster is a collection of radios that are connected purely by wireless. Once you introduce cables, if you take two radios and connect them via cable, you've now created two distinct clusters. But if we talk about a single cluster, then one radio in the cluster should be or must be designated as a POP node. Now, normally, this is the one closer to or closest to the network egress or the one connected to the fiber. And the POP node is important because the POP node is the one that initiates link ignition. As you will see in a moment, links don't just simply come up, but they're ignited in a specific order. So in order to get this ball rolling, a POP node is required to sort of, if you like, tip the first domino tile. So that's the POP-DN. So please remember, whether you're testing indoor or whether you're deploying outdoor, you must configure a POP node and just a single POP node. Okay, I'm going to skip the configuration bit, but this is what I mentioned before. Once you use a cable to connect a couple of radios, like you see here, then those become separate clusters, and each cluster then requires its own POP node. Okay, just to say, some of our radios are, I would say, optimized for operation in point-to-point or can operate in point-to-point configuration, just to make it easy for people who just want a point-to-point connection so they don't have to really worry about all these technical things. So you don't have to do things like GPS synchronization or configure a POP node on point-to-point links. This is just relevant for point-to-multipoint where this complexity is required. Okay. So let's talk about links now. So links in Terragraph have to be explicitly defined. That means, as you've already gathered, this is not a plug-and-play system. You can't just take radios out of the box, generally speaking, and expect them to link up. Now, this is not strictly true because we started selling radios in pairs for point-to-point applications where basically in a box there are two radios and they're pre-configured in the factory to just link up out of the box. So this is a really nice feature, but this is quite the exception to the rule. But generally, links need to be configured. Now, links are configured between two devices, the initiator and the responder. Now, the initiator must be a distribution node, but the responder can be another distribution node, or it could be a client node. So I've tried to illustrate the difference here using big arrows that show the links from distribution nodes to other distribution nodes, and the skinny arrows which show the connection from distribution nodes to client nodes. Okay, now the configuration of the link is done in the initiator. So basically you have to go log on to the initiator and say, I'd like to configure a link to this particular responder. And this particular responder is a client node, or this particular responder is a distribution node. Okay. Now, there is a limit on the number of links that can be configured per sector, and that is 15. So you can have up to 15 connections per sector. Up to 2 of these 15 can be to other distribution nodes. So basically, you can have, if you like, 3 different scenarios. So all 15 connections to client nodes, 1 connection to distribution node, and the 14 remaining client nodes, or 2 to other distribution nodes, and the remaining 13 to client nodes. Now, this, remember, is per sector. So if you have a distribution node with multiple sectors, obviously this scales up. Okay, now links ignite in order. So basically, a link needs to be locked upstream, if you like, in order to initiate links or ignite links downstream. This is why the POP node is so important. So here's an example. We have POP node A, and as soon as POP node A boots up, it looks at its link configuration, and it immediately, because it's a POP node, it ignites all its links to, I would say, maybe the next set of radios. So you can see that's happened here. Now, there are a couple of distribution nodes here, and only when they are locked to the POP node do they in turn then ignite their links to the next layer along, and so forth and so on. So just to say, if you are deploying a network and you're not sure why a link hasn't come up, if it's not a POP-DN, remember it's got to be first locked to upstream before it will initiate links. For example, B will not initiate links to C unless B is locked to A. Okay, so this is the domino effect that I mentioned before, and this is why a POP node is so important. If you forget to define a POP node, the process just never ignites and none of your links come up. Okay, now I've said before that links need to be explicitly configured, and you need to tell a distribution node, create a link to a particular radio. Now radios are identified by a name, okay, which means that all radios within a Terragraph cluster must have unique names, right? We call them node names or names. And you can, of course, configure that name. There's also a default name that's shipped out of the factory. That's for Siklu, that's just the last 8 digits of the serial number, which you can read off the labels. So you don't have to allocate node names, but you can if you want to make them a little bit more meaningful. So remember, when you configure a link from radio A to radio B, radio A is the initiator. In the configuration, you need to name radio B. You need to know what the node name of radio B is in order to configure the link. And the last topic in this section is SSID and password. So we have encryption built in for the transmission over the air, and the encryption key, if you like, is derived using the SSID and password. So basically, in order for a radio to connect, it must know the correct SSID and password. SSIDs tend to be known or in the public domain. Passwords tend to be kept secret. And if you want your encryption to be quite strong, then you need to select a strong password or a high entropy password, which means, with lots of characters and lots of randomness in it, because the encryption key is derived from the password. You don't have to change the SSID and password if you're not particularly worried about evil eavesdroppers. You can just leave the default because, like I said before, somebody just putting up a radio will not be able to connect to your cluster because you have to specifically go into your radio and configure a link to the radio. So they're not just going to connect, but if you wanted to protect your network in an additional layer, then use your own SSID and passwords. Okay, great. So these were some operational concepts. So synchronization, POP node, links, link ignition, and so on. And so now, hopefully, you understand a little bit how things work. And we're ready to move to what I think is the most interesting bit of this presentation, which is network design. Okay, so there's quite a lot to cover here. I'm going to talk about orientation, especially of our 4-sector distribution nodes. There's some things to know on orientation and how to optimize orientation. I'm going to mention vertical planning, that's something important as well. Line of sight very quickly, range, which I've already touched on, discuss capacity a little bit, and then move on to RF planning. Okay, so let's start off with orientation. So orientation really matters, and it's not trivial. So when you have a normal radio, most people will just have a look at where the radome is and then point the radome in the right direction. But when you have a radio that looks like a cylinder, as in the case of our 4-sector distribution nodes, then it's a cylinder and it transmits in all directions, and it's not at all clear how to orient it about a pole, for example, if you're installing it on a pole. So in order to optimize the orientation, there are 3 considerations that you need to be aware of. So the first is sector center versus sector edge. The second is the field of view because of obstruction due to the pole itself. And the last one is the number of links per sector, which I already mentioned have a limit on them. So let's start with the sector center versus sector edge. Now, this is obviously only relevant for beamforming antennas, and I mentioned that beamforming antennas are able to steer a beam within a 90-degree sector, and that's correct. However, due to the nature of these antennas, when the beam squints towards the edge of the sector, there is some degradation in the performance, and I try to demonstrate this using this graph. So in the center of the sector, there's the antenna gain is high, and then as you move away, as the beam offsets more and more towards the edge of the sector, it degrades a little bit. And so obviously, if you're using long links, if you need long links, or you have a link to a device that's particularly data hungry, then it's obviously better to have it in the center of a sector as opposed to the edge of a sector or the boundary between two sectors. And by the way, if you are using, and you should use our link budget calculator, our own online link budget calculator to do these calculations, one of the parameters that you can set is the offset, the horizontal offset in degrees, so that the link budget calculator can take into account this degradation. Right, so here's an example. So this drawing of the four petals, or the flower, if you like, in broken line, that designates the sectors, right? And it's not drawn as a circle here, just to highlight the fact that in the boundary between two sectors, the performance is not as good as the sector center. And here in green, I've highlighted a radio that's relatively far, and in yellow or orange here, I highlighted a radio that's particularly data hungry. And you can see here, they're both near the boundary between sectors. So this may not be ideal, and you might like to rotate the sectors so that these two radios now fall in the center or closer to the center of the sector, and as opposed to the edge or boundary of the sector. And this, of course, applies equally to a single sector distribution node or a single sector client node. It also has this idea of the center of the sector, where performance is better compared to the edge of the sector. Okay, so that was one consideration. Second consideration has to do with the field of view. If you place a 360 degrees distribution node at the top of a pole, then obviously it will have 360-degree view. But often people place it to the side of the pole. That's a lot more practical. And when you place it to the side of the pole, then the pole itself may obstruct the field of view, or I like to express it as cast a shadow, where there won't be any reception. So the size of this shadow depends on the diameter of the pole. Obviously, the fatter the pole, the larger the shadow. So here in this table, excuse me, here in this table are some examples to give you an idea. And with the standard bracket that we ship together with this radio, the bracket is designed in a way so that the shadow cast by the pole falls on the boundary between sectors 2 and 3. Now, this is not always ideal. Often it doesn't matter, and you can use this because the orientation is free for you to choose. But sometimes the orientation is fixed, and I'll show an example in a minute. And so if it's fixed and you actually need to transmit in the boundary between the sectors, which is not ideal, as I explained before, then there is an alternative bracket that you can request from MSDist distribution, which rotates the radio about in a way that the shadow due to the pole falls in the center of a single sector, so it only impacts a single sector as opposed to impacting more. Okay, so when would this be important? So here's an example. It's an example from central London with an application of connecting lampposts one to another. The radio here is painted in black, and Westminster Council in this case insisted that it's the orientation of this radio about the pole had to be in line with the luminaire, which is perpendicular to the road. And the application is to connect the lampposts which run along the road, which basically mean that the transmission is according to these arrows which I've drawn here. So on the left, you see what this would have looked like with a standard bracket. So the transmission would have gone exactly in the boundary between the sectors, which is not ideal. But then if you use the alternative bracket, then this is much better, because now these particular links fall within the sector center with the better performance. Okay, the last consideration is the number of links. So remember, for instance, that I told you could only have up to 2 connections to other distribution nodes within a sector. So here's an example where I need to connect 3 distribution nodes. And obviously I can't do this because I can't have 3 distribution nodes connected within a single sector. So here's another example where I would want to rotate the radio about so that one of these distribution nodes then falls in a different sector than the other 2. So that would work. So this is great, right? So remember, you've got 3 considerations to take into account when deciding what the optimal orientation is. And ideally, you should send your installer giving him the heading or the bearing of, say, sector 1. That's easiest because at the bottom of the radio, we actually engraved an arrow showing you the center of sector 1. So it's best that you tell your installer, make sure this arrow points in bearing, whatever, 73 degrees, or it points at the mini Tesco or wherever it needs to point. Okay, beginning to get a little bit worried about the time, so I'm going to speed up a little bit. Now, I mentioned up till now horizontal scanning or beamforming, but the beamforming also happens in the vertical plane. Okay, it's just a little bit more limited. It's 45 degrees or less in some models, and that means that the radio beam can scan sort of about 20 degrees above and below the horizon. And again, once the beam is offset towards the end of that vertical sector, you start getting some degradation, so it's worth knowing that. Often also, when you're going from a high place to a low place, this is just not enough. So here's an example, maybe an extreme example, when you're trying to go from the top of a building that's maybe 50 meters tall and connect some device that's on the street level. And so you see here that even at 22 degrees, you're basically reaching quite far from the foot of the building, and just this is just an example showing that there's 120 meters to the foot of the radius at the foot of the building where there's no reception because of the limitation of this vertical beamforming. So you just need to be aware of this. This is easily solved using mechanical tilt. So we've got various brackets that can tilt the radios quite a lot, up to 60 degrees if need be, so just be aware of that. Obviously that doesn't work very well for that cylinder, the 4-sector DN, because if you then tilt one sector down to the street level, obviously you tilted another sector up to the sky, which is not very useful. But it is quite great for the single sector distribution node. Okay, moving along, I mentioned line of sight before. Those of you who are not new to 60 gigahertz know that these frequencies are not tolerant to any obstruction in the line of sight. There must be a clear line of sight. So beware of moving obstacles such as vehicles, maybe tall vehicles or vegetation that tends to grow, especially in this season now. Those of you who have heard of the Fresnel zone, I just want to say ignore it in 60 gigahertz. The Fresnel zone is very, very small and it's just negligible, so no need to worry about this. In other words, if you can see the far end, you've got a clear line of sight. Okay, talked about range. I briefly mentioned that before. I just want to put it into context. So I said that when you do beamforming to beamforming, when your link is from a beamforming antenna to another beamforming antenna, that is, I would say, the worst scenario in terms of range, because the beamforming antenna is limited in radiated power, as explained by the regulator, by Ofcom, but not just Ofcom. This is not specific to the UK. This is an international limitation. So in order to extend this, for example, if you're going from a distribution node to a client node, you can change the client node to one that supports a parabolic antenna, and that will exchange your range. Obviously, the larger the parabolic antenna, the longer the range. Now, if you wanted to improve the range even more, then you can go from parabolic to parabolic, right? Because each of the parabolic antennas is then more powerful than the beamforming antennas. So sometimes we have applications where people say have two clusters. Each cluster is quite dense, but the two clusters need to connect together, and they're sufficiently far apart so that just connecting the two distribution nodes directly using their beamforming antenna is just doesn't work. So in this case, you can just use a point-to-point link with a parabolic antenna just to connect these two clusters, right? So this is the sort of thing that you can do to extend the range. Okay, I want to just say a few words about capacity. When we get multiple connections per sectors, up to 15, as I mentioned before, all these connections share the sector's capacity. Now, I didn't mention what that is. That's currently just under 2 gigabits full duplex. So if you can imagine up to 15 connections sharing a 2 gigabits full duplex, then obviously each one will get less, right? Depending on how many there are and how many are data hungry in a particular time. So now, sometimes people like to connect their network via a link to the distribution node. This is because maybe the network connection, the network egress, is not suitable for distribution node installation because, for example, there's no line of sight to all the other radios. So what I show here on the left is what we call reverse feed. So you see the network is connected through a client node, and the client node is one of many, one of three in this instance, within the sector of the distribution node. So this will work. There's no problem in that. However, you just need to be aware that the capacity of the entire distribution node, and therefore of this entire cluster, is now limited to whatever capacity the specific reverse feed link obtains, and of course it shares it with other connections. So that can become a bottleneck to the whole cluster, right? A bottleneck of all these devices and how they connect to the network. So if you are concerned about something like this, you can easily overcome it using a dedicated point-to-point link, as I've shown here on the right. Okay, so now the connection to the network is done over a dedicated link. It's not shared with anything, and then the distribution node can then share this unlimited capacity, or uncapped, I should say, capacity with the rest of its client nodes. Okay, right, we're getting to some of the most complex stuff in this presentation, but I can only encourage you and tell you that we're also coming near the end. So bear with me, please, for a few more minutes. I think this is quite important. I want to talk about RF planning. So RF planning is really designed to avoid interference in really dense deployments. Now, those of you who have done 60 gigahertz before might think, well, what's he talking about interference? We know that 60 gigahertz is inherently interference-free, and that's correct. That's because the transmission beams are narrow. The transmission decays very quickly due to the oxygen in the air, and the signal is basically killed with any obstruction. Right, so we know all that, but in addition, because I would say the people who thought up Terragraph envisioned really dense, extremely dense deployments, they worked in some other facilities to mitigate interference. I'd like to talk about that. So the first one, that's a physical one as well, is to do with polarization. So with some of our client nodes, we let you use several polarizations, as you see here. If the client node goes to a beamforming antenna, it's got to be in the vertical polarization. But if it's a parabolic antenna to another parabolic antenna, then you can use the other polarizations shown here. And obviously, using different polarizations helps a receiver filter out a transmission from the wrong polarization. That's just physically done by the antenna. Okay, but more interestingly, there are 3 Terragraph specific tools or mitigation techniques that you can configure within Terragraph on top of everything that we've just said. And these 3 are polarity, frequency channel, and Golay code. And I want to just describe to you each one of them because they are important. Just to say that you can configure these 3 things on a node level. So you can just say, well, for example, if you have 4 sectors, you can say, well, all 4 sectors, I want to configure them. I want them to inherit the configuration of the nodes in terms of polarity, frequency channel, or Golay code, but you can also override specifically per sector, and in some cases you can also override per link. So you've got a lot of granularity to play with and ensure that these tools are put to the best use. Okay, so let's start with polarity. Polarity is really important. Of the 3 mitigation interference tools within Terragraph, polarity is the most powerful one, right? So you'll always want to use polarity. You always want to start with polarity to ensure there's no interference. So what is polarity? Polarity is essentially the phase of the GPS clock. So remember we said all these radios need to be synchronized to the GPS clock, and this is why. So some radios will be configured to even polarity and others will be configured to odd polarity, and these are just labels. Don't read into these words too much. The point is that even polarity radios all transmit at the same time slots and all receive at other time slots, while the odd polarity radios are complementary. So when the even polarity radios transmit, all the odd polarity radios receive. And conversely, when all the odd polarity radios transmit, all the even polarity radios receive. So some radios will have odd polarity, some will have even polarity. And the point here in terms of interference mitigation is that 2 radios with the same polarity can never interfere with each other. So for example, if you've got 2 radios with even polarity, they both transmit at the same time and they both receive at the same time. So they can never hear each other, right? They can never interfere with each other. And this is really, really powerful. So here is an example. Here's a simple network. We've got 3 radios A, B, C. A wants to transmit to B and B wants to transmit to C. Now, C obviously only wants to hear B, but if all these radios are quite in close proximity, then A is a potential interferer, right? C might receive the signal from A, which is an unwanted signal and a potential interferer. So what we do then is we alternate the polarities as shown here. So A would be even, B would be odd, obviously because B wants to hear A, so B needs to be different than A, so odd in this case. C wants to hear B, so C needs to complement B. If B is odd, then C needs to be even. Now C is even and A is even, so A can never interfere with C because A and C both transmit at the same time and they receive at the same time, right? So A essentially cannot interfere with C. And this is absolutely true, okay? So because this is all synchronized to the clock, which is absolute, and so you can rest assured you will have absolutely no interference from A to C, the most powerful interference mitigation tool. Now, we recommend, therefore, to alternate these polarities as you go down your network tree, as you see here. So even, odd, that's sort of the correct thing to do. And on the left here, I've drawn an example where we have 2 distribution nodes that are connected to each other, and therefore there's an overlap in their respective sectors. And there's a client node in the middle, and the client node wants to talk to A. Right, so we configure the link from A to that client node. And the question is, well, that client node falls easily within the sector of B. Why doesn't B interfere with it? Well, exactly that, because A is even, so the client node will listen in to even transmission. That means it will become odd, and so it will never hear B. Now, I may have mentioned it, I don't remember. These 3 parameters, polarity, frequency channel, and Golay code, which I'll talk about in a minute, you only need to configure them for the distribution nodes because the client nodes or the responders automatically pick up on whatever the initiator is doing, right? So only the initiator matters. Okay, so hopefully you understand polarity now. Next, we move to frequency channels. We recommend alternating. So our portfolio supports 4 channels, and we recommend alternating them, as you see here. For example, channel 2, channel 4, channel 2, channel 4. Obviously, the sectors are not as beautifully demarcated as I've drawn them here, because there will be some leakage from one to the other, and this is why we like to have different channels. So how does this work? So here's the same example as before, but I've added a 4th radio, right, radio D. Now D wants to hear C only, but C is even, so D obviously has to be odd, right, to hear D. D has to obviously be odd to hear C, but A is also even. So A now becomes a potential interferer, right? If A is close enough to D, A will interfere at D. And so to prevent this, this is where you use another mitigation tool such as frequency. So for example, if I used channel 2 at A and B, then I might use channel 4 at C. So then D will only look out for even transmission on channel 4. A is doing even transmission, but on channel 2, so A will be blocked out. So hopefully this starts to show you how you can mix and match these parameters. Right, time is up, dear me. So I will very briefly mention the third one. The third one is quite technical. It's technically, it's called the Gole code. And just to say, it's another mitigation. It's a form of error correcting code that helps a receiver block out unwanted transmission. And you can just use different Gole codes to avoid this kind of interference. So here is the same example as before, but let's just suppose that we only have access to channel 2. We don't have other channels for various reasons. So you can still avoid interference from A to D by simply using a different Gole code at C. So D will look out for Gole code 2. If A is doing Gole code 1, A will not be able to interfere with D. So I think we need to stop here because it's 4 o'clock. So I am just going to fast forward this a little bit and take some questions for those of you who can remain after 4 and have questions to ask. Those of you who have to go, thank you very much for bearing with me this past hour, and do get in touch with any feedback or questions. Right, Ian, over to you.
Daniel, we've got some super interesting questions. Chris asks, if a radio product meets 802.11ay standard, would it be automatically classed as a Terragraph certified product?
That's a very good question. I'm not sure. I think the answer is yes, but I'll need to look it up. And
yeah, oddly, I didn't know the answer either, Daniel, and I was sitting here thinking, I hope Daniel knows the answer. We'll find out and let you know.
But it is worth mentioning perhaps that there are different levels of Terragraph compliance. So Terragraph is actually designed as a layer 3 network, and some vendors, Siklu included, decided to opt in for a layer 2 as opposed to layer 3 network. So there are different degrees of Terragraph compliance, and certified is one of them. And yeah, just so you know.
Absolutely. So Nigel asked, would we make the slide deck available for people along with the recording of the webinar? And I said, yes, of course we would. So that's done. Tim asks.
So just to say about this, so I mentioned this before, these slides are all taken from an e-learning program, which we're putting together, and we hope to be able to launch maybe in 3 weeks or so. And it will be, it's a great course actually, where everything I've shared with you now is just a part of that. There's lots of hands-on stuff on there as well. So please do, in 3 weeks time, I'm sure our great guys at marketing will blast it to all of you and let you know when that's alive. And then you'll be able to access these slides and actually go through these modules and also get Siklu Terragraph certified.
Marvelous. Tim asks, does the DN meshing auto repair if one of the nodes goes down, i.e. does it reroute?
So the answer is no. There is a facility to do this, but this requires an external controller. which is not quite ready yet for Siklu. So this is coming out over the next couple of months, I believe. And it's called Smart Hall. Smart Hall is that collection of software tools that will be able to repair, if you like, broken connections on the fly.
Mike asked, what's the paint color?
You can use any paint that you like, just make sure it's metal free, and apply a thin coat, right? Don't slap it on with paint. You can also use vinyl if you need a particular picture. If you would like to disguise the radio, say it's next to a brick wall, you can wrap it with a vinyl with a brick pattern on it. But again, metal free.
I think he was specifically asking what does it come natively, and I'm sure there's a RAL color to it. We'll find out what it is.
Oh, it's an off-white. It's just an off-white cream color.
Sure. Nigel asks, you mentioned about oxygen absorption. Can you describe if there's anything else that causes interference, i.e. rain, snow, fog, if someone's heavily vaping underneath it, or indeed if there's lots of pigeons? He didn't say those bits, I've just made those up. But let's assume we're in Trafalgar Square and there's lots of pigeons around. Is anything else affecting the ability to be able to transmit?
Transmission. Yes. So rain is the arch enemy of millimeter wave frequencies. So in longer distances, longer ranges, it does become the most significant, I would say, attenuation or adverse propagation factor. So you need to use our link budget calculator, which we have online, with long links. If you're doing short links up to say 200 meters, 300 meters, then the rain won't really be very meaningful. You can still, the link budget calculator will still tell you what it is, but just practically speaking, it's not very meaningful. But for longer links, if you're using parabolic antennas for longer links, do look at what the rain will do. The other things that you mentioned, no, things like fog, smoke, the particles are too fine to obstruct 60 gigahertz transmission. The radios get very hot, and so we don't normally get birds perching on them or staying too close to them. And if there's just a bird flying in the line of transmission, they're usually too small to cause any problem.
Brilliant. Chris asks, and he's left, so he'll have to catch up with the recording. We've mentioned even and odd polarity. Does that mean that the link's operated in half duplex?
Yes. So Terragraph is a TDD and TDMA system. So basically we have a distribution node that can connect to up to 15 connections. And so it does that one at a time, right? So the beam will automatically go to one, then to the other, then to the third, and so on in a round robin type of fashion. So yes.
Brilliant. Todd says, absolutely fabulous presentation. Thank you very much. You're very welcome, Todd. Do come and talk to us later. Itor says, I missed the capacity per sector. Can you tell us what the capacity per sector is, please?
Yes, so at the highest modulation, it's 3.8 gigabit per second aggregate, which translates to 1.9 gigabit full duplex. So that will be what you'll get with a point-to-point or per sector. And if there are multiple devices per sector, they will share this. And just to say, we are going to bring out a feature called channel aggregation in a few months' time, and that will not quite double that, but I think will significantly increase it, probably maybe from 1.9 to 3 gigabits per second per sector.
Brilliant. Nigel says, really enjoyed the webinar, thank you. Hamid asks, can we have a redundant POP node to avoid the domino effect if a POP node is down?
Yes, you can do. Obviously, this will all work better and seamlessly with Smart Hall once that's available. But you can even do so now. So you can set up two distribution nodes and configure them both in an identical manner and to link up to all your client nodes. And what will happen then is that the client nodes will only lock to one. It's a bit random which one they would lock to. And then if that were to fail, then they would obviously look out and then lock onto the second one. Yeah,
absolutely. Moving on to Professor Tim Porter, who's being a little mischievous and asks, The real question is, can MikroTik 802.11ay terminal device talk to an N366?
No. So the answer is no. So like I said, there are different levels of Terragraph certification, and where we are, which is Terragraph certified, there's no interoperability with other vendors.
Absolutely. And all I can say is, Tim, you're a very naughty boy. Anthony says Terragraph is 802.11ay. Not all .11ay will work with the Mac and Phi on a QCA chipset. So there's an answer to a question that came in earlier, which is really rather nice to have somebody else with us that understands the stuff that we're at chipset level. Will there be any near future firmware updates that include SNMP, NTP, DHCP, etc.? And that's come from Pedro.
Yes. So these things are definitely on the roadmap. I believe SNMP is the first to come along. I don't remember exactly when, but it is sort of within the next 1 or 2 releases. But Pedro, please, if you get in touch with us, we can share the roadmap with you specifically about these features.
And similar question, and actually it's the final question, does talk about firmware as well. Todd says, time permitting, would you talk a little about what customers can expect when it comes to a software release schedules and what upgrading firmware looks like? So if we've got a firmware upgrade that is on a customer device, what does that look like?
Yeah, okay, so that's a very good question. First I'll answer the easy part. In terms of practically upgrading the software, that involves 2 steps, or I should say 3 steps. One is obtaining the software image from Siklu, so either from our partner portal or from our FTP server. 2 is copying that file to the radio itself. And 3 is then causing a reboot for the radio to boot up with a new version. So the last step there, the reboot, is obviously traffic affecting for the duration of the reboot, which is approximately 2 minutes, and you can schedule it for non-peak hours if you wanted to, say midnight or whatever. So this was the practical side of it. In terms of schedule of releases, so I am expecting at least 2 more releases, if not 3, by the end of the year. The reason is that we keep releasing new products into the portfolio. For example, we just released a point-to-point package, and we released a single sector DN. So obviously, all of these require new software versions to support them. That's reason 1. And reason 2 is that broadly speaking, this is a new technology. Terragraph we only launched it at the beginning of last year, I believe. So there are still numerous number of bugs being discovered here and there. And so obviously we're working as fast as possible to patch them. So when we discover important things or things that we think will impact a lot of customers, then we might push a release out with a fix prior to its natural schedule.
There's 3 more questions. Well, there's not 3, there's 2 more questions. Kennedy asked, can I consider Terragraph as an alternative to FTTX? And the answer is absolutely you can, given a certain set of circumstances, but come and talk to us and we'll tell you what those circumstances are and how that works. But goes on to ask in a subsequent question, can you touch on the different types of Terragraph certifications?
No, unfortunately, I don't know them off the top of my head. If you though, you take the gentleman's name, then I'll be able to respond by email.
Yeah, that's Kennedy. We'll pick that up and get an answer. Peter in the middle of that said, thank you very much, really informative, much appreciated. You're very welcome, Peter, although I think he possibly left. No, Peter's still with us. And final question, I think it really is the final question, Daniel, you'll be pleased to know. Is it just the DNs that need NTP via GPS? I think you said, but could you use DN indoors and NTP sync it via an internet connected NTP server? So could you, in theory, use the product indoors under certain circumstances, or is the requirement for NTP stratum 1? Question.
Okay, wow, so that's a very good question. So just to say, the requirement for the GPS connection is to derive the actual clock frequency as opposed to the time of day. So NTP is a protocol that broadcasts time of day. If I have my laptop and I wanted to, have an accurate clock, then my laptop would use NTP to derive the clock from some, as you said, Stratum 1 server. But here the problem is different. Here we're not interested in the time of day. We're interested in the actual frequency of the clock itself, of if you like, the ticks of the clock. And so that cannot come over NTP. That must come directly from the satellite. And that's why these radios cannot be installed indoor. Having said that, there are particular or limited circumstances, such as a point-to-point or doing a single sector that you can do indoor.
Well, that's the end of the questions, Daniel. And I think thank you very much to, no. Will you recommend Terragraph for community municipal-based wireless ISPs? Distinctly possible, Kennedy. Probably the best thing to do is to come and talk to either us here at MS Distribution or get in touch with Siklu, and we'll talk through the specific use case. Nigel, you're very welcome. Listen, I think we've had some really interesting people listening to the presentation. They've all been super enthused. They've asked some really good questions, Daniel. I think you'll agree with me.
Absolutely.
So thank you very much.
Thank you, everyone.
Yeah, thank you very much for joining us today. We really appreciate it. Obviously, as we say, we'll get whatever slides we can to you. We'll get the recording to you. We're all looking forward now to certificated training. Daniel, thank you very much for doing that pitch for us. Obviously, we'll bring that to you via MS Distribution and Siklu at some point in the near future. Really appreciate your time today, guys. Sorry we're a little bit over, but I think it's really been worthwhile to understand a bit more in depth underneath the bonnet of what actually goes on with Terragraph and how it's deployed. Super impressed with our presentation today. As always, Daniel, thank you so much. Really appreciate your time. If you need anything better, deeper, harder, faster, whatever it is, guys, do come and talk to us. I think we ought to end now, because otherwise I'll just ramble on for hours and hours and hours like I do. I'm going to stop. Thank you so much for joining us all, and speak to you again soon. Take care now.
Thank you very much. Bye-bye.